Hello everyone, welcome back. So today's problem is from statics and just a little bit of magnetism. So in the question we have a flexible conducting thread whose length is L and through which a current I flows. It hangs in a horizontal uniform magnetic field of induction B. Both ends of the thread are suspended from practically the same point A. Okay, so basically this thread over here, which is in the shape of a teardrop, it's suspended at this point A. In the equilibrium position, these ends form an angle of 60 degrees with each other, and the distance between the suspension point and the lowest point of the thread is capital H. The acceleration due to gravity is g. The current's own magnetic field can be neglected, and the thread is uniform. So this basically means it's the mass distribution is uniform. So and then we need to figure out these three questions. So we have to find the mass of the thread, tension at point D and C, and we also need to figure out this distance small d. Okay, so that's a question. So give this a try, guys, and then check out the solution. Okay, so for the first question, we need to figure out the mass m of the thread and the tension at the lowest point, which is TD. Okay, so as we need to figure out the tension at the bottommost point, we'll start by taking the half FBD. So I'm just going to consider half of this thread and draw its free body diagram. Okay, so let's say this is the half FBD, and so we have the point A over here and the point B over and the point D over here. Okay, so firstly we'll have the tension force at the point A, and this would make an angle of 30 degrees with the vertical. Okay, and this is because the angle between these two ends were given to be 60. So if you extend this part and drop a vertical, this angle will be half of 60, which is 30 degrees. Okay, so therefore the tension TA makes an angle of 30 degrees with the vertical. At the lowest point, the tension TD is approximately horizontal, so the tension TD will be in this particular direction. And then we have the force of gravity. As it is the half FBD, its weight will be half of it, half of the total, which is mg over 2. So now all that is left is the force due to the magnetic field. So the current was flowing in this direction. So the current in the wire is flowing in this direction from D to A. So first let's just take a random element somewhere over here. So I'm considering its length to be some delta L. So it's very small, so that you can basically consider this as a straight line. Okay, and neglect its curvature. So if we have a current element, okay, so if we have a current element that is placed in a magnetic field, the force it experiences is given by I delta L cross B. Okay, so the current flow is in this direction and the magnetic field is out of the page. If you do I cross B, the direction will be in this particular direction, perpendicular to, which is basically normal to this element. Okay, so the force on this tiny element will be in this direction and its magnitude will be I B delta L. Okay, similarly you can consider this as a cluster of delta L's, and each of these elements will feel a outward force, and similarly on the other part also it will feel an outward force. So now let's observe the delta element a bit close. So if this is the element and the force is in this direction perpendicular to the direction of delta L. Now the thing is, if let's say we want to figure out the x component and y component of this particular force, so we'll try to figure out this particular angle, right? So let's say this angle is theta, then the y component of this force will be IB delta L sine theta, and the x component of the force will be IB delta L cos theta. Okay, now similarly if we resolve the vector delta L, as the normal makes an angle of theta with the horizontal, delta L vector will make an angle of theta with the vertical, so this is going to be theta as well. From this right triangle we can see that this length over here is delta L sine theta, and the height is the delta L cos theta element. If I name this as delta x for a second and this as delta y for a second, then what I can see is delta x is delta L sine theta and delta y would just be delta L cos theta. So instead of delta L sine theta, if I write it as delta x, the y component of the force will become IB delta x and the x component will be IB delta y. Okay, so simply speaking, this y component will be IB delta x and the x component will be IB delta y. Now this is going to be very useful because what this essentially means is that if we consider 2 points on this wire, which can be far apart as well, and if we just want to talk about the forces in the x direction, the net force on this part, it will be just the summation of ib delta y, or you can just say integration of ib dy. They're both the same. I, which is just ib times sigma delta y. So all you have to do is add the delta y's of these elements, which basically will end up as the y coordinate difference between the 2 points. So this will just become ib times, let's say, y2 minus y1, which is basically the difference in y. Okay, so this is going to be very useful in this question. Okay, so now let's look at the half FBD. So if you observe something, the point A and the point D are on the same vertical level. So if I talk about the total magnetic force on the half FBD, it won't have any vertical component. And the reason for that is the vertical component is given by IB times the delta x between the 2 points. And as both these points have the same x coordinate, there won't be any y component. Okay, so intuitively it's because if you observe at points that are a bit lower, the y component of the force is negative, and at points above the y component is positive, so they mutually cancel each other out, and hence there is no component in the y direction for the magnetic force. Whereas for the x direction component, it is ib times delta y, and the y coordinate difference between point A and point D is just capital H. And intuitively we can see that the x component force is towards the right, so the total magnetic force in the rightward direction is going to be IB times capital H. Okay, so now basically the FBD is done, so now we can just balance the forces. So if you balance the forces in the vertical direction, we'll see TA cos 30 equals mg by 2, and if we balance the horizontal forces, we'll get TA sin 30 plus TD would equal IBH. Okay, so now if we observe something, we have two equations and the variables are TA small m and TD. So we have three unknowns and just two equations, so we need to figure out one more equation. So we already used fx equals 0 and fy equals 0, and the third relation is going to be a little bit tricky. Okay, so what we're going to do is we're going to once again consider a tiny element on the wire somewhere over here, and let's say this is point P1 for a second, and let's say the next element is P2, and so on and so forth. Okay, so once again let's draw the FBD. So this is the first current element. So once again it will have the magnetic force in the normal direction, whose magnitude is IB dl if the length is dl. Okay, and at both ends of the wire there's going to be some tension forces. So I'm going to consider the tension at this end is T. Now guys, of course there is going to be some curvature of the wire, otherwise the forces won't be balanced in the normal direction. So it's not like perfectly parallel, but the curvature is so negligible that we can kind of ignore it as we are considering a tiny element. Okay, so and anyways the curvature isn't important for the current analysis. And let's consider the tension force here as T plus dt. Okay, I'm considering the tension here as T plus dt because it's intuitively clear that the tension at the higher point is higher. And then we have the weight of the element, which is going to be the mass per unit length times the length of the element times g. So this is the FBD of the element. So now let's say this angle is theta, then this angle is also going to be theta. Okay, so now what we are going to do is we are going to balance the forces parallel to this particular direction, which is parallel to the DL element. So this way we can ignore the IB DL element. Okay, and let's see what we get. So we get T plus dt, which is the uphill force, equals the downhill force, which is T plus lambda dlg sine theta. There won't be any IBDL component because IBDL is perpendicular to the DL vector, right? So from here the T cancels out and we get dt equals lambda g dh. Okay, so DL sine theta. So from this triangle, DL sine theta is just dh, which is the small change in the height which is basically the height difference between these 2 points. So what we are seeing is that if we move from point 1 to point 2, the increase in the magnitude of tension is lambda g dh. Okay, so now let's say the wire looks something like this, and we go from point 2 to point 3. Then once again the tension increases by lambda g dh, and if we keep on doing that again and again, or in other words, if we just integrate this expression from the bottommost point, which is d, and let's consider the height there as 0, and we move till the topmost point, which is a, and the height there is obviously capital H. What we get from here is that TA is equal to TD plus lambda g capital H. So this basically gives us the third required relation between the tension at point A and the tension at point D. Okay, so now there is another method to reach the same relation, and that's by using the method of virtual work. So let's say we have some kind of point particle over here, and let's say some forces are acting on it in some arbitrary directions. Let's say F1, F2, and you can consider any number of forces acting on this particle. But the condition is that this particle has to be in equilibrium. So what that would mean is the summation of all the forces, right? So on until Fn, they should vectorially add up to 0, right? Or in other words, sigma Fi should be 0. Okay, so this is the condition for equilibrium. So now let's say we consider a small displacement of this particle, okay? And let's say the displacement is some delta r, okay? So delta. So now here the work that F1 does will be F1 dot delta r, and what F2 does will be F2 dot delta r, and so on and so forth, right? So the net work here is just F1 dot delta r plus F2 dot delta r, and so on for all the terms. And from here you can just take the dot product dot outside, so this would be just F1 F2 and its sums dotted with delta r. Now here you need to observe something. The reason why we can take delta r outside is because the point of application of all the forces are the same, right? So if the forces act at different points, then of course the works due to each forces will be different. It won't be dotted with delta r. It will be dotted with the displacement of the point of application. So in that case, it will be F1 dot delta r1, F1 dot delta r2, so on and so forth. But yeah, if the displacements of the point of application are the same, we can take the dot outside. And if you observe here inside the bracket, we have the summation of all the forces, and this would just be 0 because that was the original condition, right? Now this method is also used in another context where we have to like find out acceleration after immediately releasing a system. But yeah, that's probably for a different video. Here we are dealing with static equilibrium. So yeah, this is basically the idea. So we'll say that if we imagine a small displacement of delta r, the total work done by all the forces acting on the system for the small displacement will be 0. Okay, so this is the logic we'll be using. But we'll also have to be careful of this particular fact that delta r's should be the same. The displacements should be the same. Otherwise, the works would be different, right? Otherwise, the virtual work won't be 0 necessarily. So this is where we use a slightly tricky idea. So I have to consider a displacement. Okay, so now the question is, how should I consider my small displacement so that I can take the dot displacement term outside? Okay, so this is the tricky part to this method. Okay, it's a bit intuitive if you observe. So observe this point A here. So what I'm going to do is I'm going to displace this point using my imagination by a small amount of, let's say, dl. Okay, or you can also use the delta symbol, but doesn't matter. So I displace it by a small distance of dl. Okay, now if we displace it by a distance of dl, then as the length is constant, we'll have to move the dl at some other point. So how we are going to do it is that we maintain the orientation of every other point as such Okay, so we basically don't move it in the normal direction. We keep the orientation as such, and we'll just displace the point D by a distance of dl in the rightward direction. Okay, so basically the string length, we pulled it in this direction by an amount of dl, and the point D we move towards the right by the same amount of dl. Okay, and every other point on this wire will look identical to the previous case. Okay, so now let's write down the works in this particular case. So if you observe, now in this case, tension TA was acting in this direction. So the work of tension TA will be TA multiplied by dl. Okay, so it will be obviously positive. And here the work of tension TD will be negative TD minus TD And the logic for keeping the orientation fixed was that we can avoid the work of the magnetic field, because if you observe, the magnetic field is normal to the wire at each point. So if you move the wire in the tangential direction, there won't be any work of magnetic field. So that was the logic of keeping the wire in the same orientation and just moving the endpoints by a small distance. Okay, so the work of magnetic field is just 0. Now what about the work of gravity? The work done by gravity, we can link it with the change in potential energy, change in gravitational potential energy of the system. So if you compare the before with the after, like the only difference is that a small dl element which was present at the bottom over here got transported to this particular point over here, right? So a small dm mass from here got transported to a height of capital H. So the potential energy increased. Okay, so basically the work that the force of gravity will do is minus dmg multiplied by capital H. Okay, so basically the dm mass which was present over here, it got transported up by a height of h. So the increase, okay, so the work done will be dmg multiplied by capital H. Okay, so now the mass dm is just lambda multiplied by dl. And so this is the total works of all the forces, and this should be 0 for this very tiny displacement. Okay, so this would be, okay, and from here we get the same relation, ta equals td plus lambda g capital H. So yeah, in some questions you can utilize this method but yeah, you have to observe, how to do the displacement. Okay, so now we basically have 3 equations, and basically we have 3 variables, so we can just solve for each of them. And once you solve, you'll get you'll get these 3 expressions for TA, TD, and small m. So yeah, that was the first question. Now for the second question, we have to determine the tension at the extreme right point, which is C. Okay, so we have to figure out the tension at this point. So as is the extreme right point, here the tension will be approximately vertical. Okay, so now you can consider either, okay, so now we have to section the wire at this particular point to figure it out. So we'll just consider this FBD of the section DC, because now we know the value of TD. Okay, so at the point C, the tension is vertical, so TC. And at the bottommost point, we know that tension is almost horizontal, so that is TD. Now the thing is, we don't know the height difference between these 2 points. X coordinate difference would be d by 2, but d is also something that we have to figure out. This height, we can just say it is some h, and we also don't know what is the mass of this section. Okay, so let's just write down the forces first. So now the force due to the magnetic field will have 2 components, one component towards the right and one component in the downward direction. And we figured out that the x force is decided by the y difference, so this will be IBH, and the y force is decided by the x difference, so this is going to be IB times d by 2. And we also have the weight of this part, which is just, let's just write it as m dash g. So now if we balance out the x forces, we get TD equals IBH. TD was IBL by 4 root 3, so you'll get h as L over 4 root 3. So now we know the value of h. Okay, so now if you remember this particular relation over here, we can basically use this for any particular point. Okay, so you can consider any 2 points over here. Now the difference between the tensions at these 2 points will be a factor of lambda gh, where h is the height difference. Okay, so here also we can use the same thing. So we can say Tc is nothing but the tension at the bottommost point plus lambda g times the height difference, which is h. Okay, and after substituting, so here instead of lambda, it will be m by L, and m times G I can write it as IBL. Okay, so yeah, after doing the manipulations, you'll get this as the answer. Okay, so that was the second question. Now in the third question, we have to find the distance D. Okay, so we already have the FBD over here. So IBD by 2 plus m dash G will be equal to TC. But the issue here is that m dash is something that we don't know, right? And the only way to really find out m dash is by finding out the length of this segment of the wire, which is going to be an annoying integral. So another way to think about this is to somehow find out the trajectory, somehow move in the direction of finding the trajectory of this segment, because let's say we call this point as 0 comma 0. This point will have a coordinate of h comma d by 2, right? So if we somehow figure out the trajectory, let's say, as we know the x coordinate, we can figure out the y coordinate. So we should be moving in the direction of finding the trajectory somehow. So yeah, so for that, we'll just take a random point and say the coordinate is x comma y over there, and I'm considering the origin to be at the bottommost point. And if, okay, and now if you consider the FBD of this part, and say we consider the tension at this point as some T, and now let's balance down the forces for this element. Let's just also consider the angle with the horizontal as theta. Okay, so basically theta is the angle that tangent at this point makes with the horizontal. Okay, so basically if we consider this as a curve, okay, so dy by dx at this particular point is going to be tan theta. Okay, so now let's balance the forces in the y direction. So we have t sine theta in the upward direction. So first we have the tension relation that we figured out earlier. So T is nothing but TD plus lambda G Y, right? So in this case, it will be lambda G Y. Okay, so now the next relation is the force balance in the Y direction. Sine theta, so this is the vertical component of tension, would be equal to the weight of this part, which is going to be lambda G times the length of this element. Okay, so let's say the length of this part is some L. Lambda GL would be the weight of this element in the downward direction. And then we also have the magnetic force. Okay, so the magnetic force in the Y direction will be equal to IB times the x coordinate difference, which is just x. So this thing plus IB x. Okay, so now the thing is, guys, IB into L, we can just was just equal to mg. So I times b is just lambda g. Okay, so instead of this, we can just write lambda g, and this would be lambda g times x plus L. And what's left is the x direction force balance. So that would be t cos theta would be equal to plus IBY equals TD, and IB we can write it as lambda g. So these are the three relations that we have. We somehow need to do some manipulation and get rid of the tension and just reach to an expression with just x and y terms. Okay, so one way of thinking can be that we figure out t sine theta is equal to this particular thing. T cos theta, you can take this thing to the other side, and then you divide these two equations. So what you obtain is tan of theta is lambda g multiplied by x plus L divided by TD minus lambda gy. But the issue with this is that we have a term containing small l over here, okay, which is once again a variable, right? So this will just add another layer of difficulty into this expression. So therefore, this is not a good idea. So what we can instead do is, as L is a bit annoying to deal with, we can just differentiate this expression so that we only have to deal with differential elements. So I'll just differentiate first the second equation. So we have, as t and sine theta are both variables, I'll just leave it as such. So this will be d of t sine theta, and on the right side it will be d lambda g multiplied by dx plus dl, right? Okay, so dl would be in this particular direction, and theta is the angle it makes with the horizontal. So dl cos theta would be dx, and dl sine theta would be dy. Okay, so this would be equal to lambda g times dx plus, instead of dl we can use dx over cos theta which would become lambda g 1 plus cos theta over cos theta times dx. Now, of course, we can't integrate this. We have to do some more manipulation. Differentiating the first thing would be useless. Differentiating this won't be that helpful either, because we'll get d of t cos theta and d of t sin theta, which we can't do anything. But if you observe, if you add the first and the last relation, we are getting a 1 plus cos theta factor, which is also present over here. So if we add equation 1 and equation 3, what we're obtaining is t 1 plus cos theta, and the lambda gy just cancels out, equals 2 times td. So this is the equation that we're obtaining. So instead of the 1 plus cos theta, we can write down this particular thing. Okay, so now once we did that, there is a factor of td over capital T over here. Now here the variables are capital T, cos of theta, and okay, so there was a dx here as well. Okay, and we'll have to be integrating it with respect to x. If we take the t to the other side and cos theta to the other side, we'll have t cos theta multiplied by d of t sin theta equal to this thing. Now if this was this cos theta was equal to sin theta, then this would have been a very easy integral. Okay, so what I'm going to do is multiply both sides by tan theta. So now this tan theta will multiply up with the cos theta to give sine of theta. And on the right hand side, if this is dx and this is theta, dx times tan of theta is just dy. So this thing will just become dy. And now if you observe, it's a very easy integration. So this thing over here is just a constant. The left hand side is just the x dx integral. So this will be x squared by 2. And the right hand side, instead of lambda g, we can write it as ib. And the td value we can just substitute. Integration of dy is just y. Will be integration of dy. After evaluation, it will be just y minus 0, which will be y. And the value of theta at the bottommost point is 0. And at y, we consider it to be theta. So this will just be t sine theta whole squared by 2. So after taking the square root, this is what we get. So now we have t sine theta as a function of y. Okay, so now now if you observe the t cos theta expression, it was td minus lambda gy. Okay, so this is the t cos theta expression. So if you substitute the values individually, it simplifies as this expression. So now the thing is, if you divide these two expressions, the left hand side becomes tan of theta, which we can just replace with dy over dx, and the right hand side becomes into this particular term. Okay, so now we can just separate variables. So dx on one side and dy on the other. Okay, and once you separate the variables, you can just integrate it. So at y equal to 0, the value of x is also 0. And at the value of y equals small h, the value of x is d by 2. So after solving, so now we can just integrate it. Yeah, actually guys, as we know that the value of h is L by 4 root 3, we can just simplify the integral a bit. We could have just substituted this thing as h initially itself. So let's just quickly do that. So then it becomes h minus y dy divided by, now this thing also can be modified a bit. So if I multiply it with 4 and take a 2 outside, the L by 4 root 3 would be h. So this is just square root of yh. Right hand side is just d by 2. So now we can just integrate this. There would be a 2 here as well, which was this 2. And this is just integration from 0 to h. Okay, so this evaluated would be h minus h by 3, which would be just 2h by 3. And this would be equal to d by 2, which means the value of d is 4h by 3, which would be L over 3 root 3. Okay, so this would be the final value of d as well. Okay, so yeah, the last part was definitely a bit tricky, because we had to do some manipulations to get to deriving the trajectory. So yeah, that makes it definitely a bit tricky. So yeah, that is it for this video guys. If you have any doubts, you can comment down below. And if you enjoyed the video, make sure to like, share and subscribe. And that's it. Thanks for watching.